Hello everyone, I'm Carla Fabiana Chiesserini, Politecnico di Torino and CNIT, and I have the pleasure to introduce the Crowdsourcing AI from the ADROIT6G European project. Here is what we are going to discuss today: context, crowdsourcing AI, what it is and why we introduced this concept, and then crowdsourcing AI in action through the merge framework and the impact that this can be.
Vai avanti, poco avanti.
Ah, ok, allora vabbè, ora l'inizio perché...
Se l'inizio poi ci ti fermi.
Vado avanti, ok. Hello everyone, I'm Carla Fabiana Chiesserini from Politecnico di Torino and CNIT, and I have the pleasure to introduce the concept of crowdsourcing AI developed within the ADROIT6G European project. What you are going to see today, first of all, some context, what the crowdsourcing AI concept is and why we introduced it, and crowdsourcing AI in action through the merge framework, the impact that this can have on the system KPIs, and finally the integration in the ML ops pipeline. So let's start with some context. We know that AI ML has become pervasive, and in order to use AI ML, we typically need to implement an ML pipeline that includes the use of data, extraction of features from the data, and then according to a supervised training approach, we use the features and the labels to train a model. Once we reach convergence, then the model is ready to be used for inference and therefore to produce a prediction. Now, very often, this pipeline, in particular training, requires a high computing resources available, and inference is typically lighter, but still it needs to be repeated many times. So in the end, the ML ops pipeline is actually quite costly in terms of resources. And this is clearly an issue when we are operating in particular at the edge nodes that are resource constrained. So we need to make AI ML feasible and to make it feasible to be executed at the edge and sustainable. That means to reduce the energy consumption due to the execution and, of course, training of the machine learning models. AI as a service is also a promising paradigm because it allows the edge nodes or user nodes to download ML models for inference. These models should be already trained, but edge nodes very often have to customize these models using their own data, and this data may be private. Also, nodes are heterogeneous with different capabilities, and this means that typically no size fits all. So through crowdsourcing AI, we are able to address these challenges. What is crowdsourcing AI? This is a simple example that shows how it works. Let's start with a user that has trained a model locally. This model can be a DNN or a resource or a reinforcement learning model. And after this local training and usage, then the user can upload the model to a common repository. Another user that requires a similar model for the same task can download this version of the model, use it, or possibly refine it and use it, and then upload it again to this common repository. And this may repeat several times. Every time we get a new version of the model, the common repository is going to store all these different versions. So the end users and edge nodes that need to execute the model may be, of course, of different nature with different capabilities, as shown in this picture. So the concept is quite simple but very effective. It's like when one borrows a book from the library and then enhances the model, the book, with a couple of pages, and then it returns the book to the library. So we collaboratively enhance our model. Crowdsourcing AI, therefore, allows for the sharing, reuse, and refinement of the knowledge in an environment that is distributed and may include heterogeneous nodes with different constraints in terms of resources. So it realizes AI as a service, but more effectively and efficiently. And indeed, we have the possibility to create several different versions of the same model that have different complexity. So they are going also to demand for a different amount of resources, still achieving the target KPIs we are interested in. It contributes to privacy preservation because these new versions of the models that are created using data locally. So the model is fine-tuned at the edge nodes or user devices, and data are not shared. It is highly flexible, as already remarked. It can work with reinforcement learning and DNN models, and is extremely flexible. It can adapt to different environments, constraints, or requirements from the application point of view. As a further remark, unlike federated learning, it allows for reuse and sharing of knowledge for which federated learning has not been designed. Now, crowdsourcing action, the merge framework. It is a framework based on meta-learning for distributed crowdsource AI model creation, adaptation, and selection. The goal is to match the node's computing capabilities and, of course, the requirements in terms of target KPIs, time for training or refinement, and accuracy level, for example, in a classification task. It leverages existing techniques like pruning, distributed learning paradigm, and meta-learning. But at the same time, it actually bridges the existing research gaps. For example, pruning often suffers from model localization. Distributed learning does not support by design customization of the models, and meta-learning is often hard to implement and was not used for resource allocation earlier. If you are interested, you can also refer to our paper on merge. This is the representation of the scheme, where the core components are the models repository, the model maker, where we have the deep reinforcement learning agent, that is the brain of merge, and the aggregator. The goal is to create a model that is suitable for the functions that we need to perform at the radio interface. This scheme applies to the scenario where we have a centralized unit, distributed unit, and radio units, but merge is general and can work in any radio interface. So we have the repository where there are models, different versions with different size and therefore complexity. And of course, they may also be apt for different tasks. When we have the need to create a new model to be run at the radio interface, we have the DRL agent that, as I said, is the brain of merge that needs to decide how many versions of the models should be combined in order to indeed merge the knowledge that has been collected in the system so far. And the versions, existing versions of the model that are stored in the model repository are selected in order to maximize reward that accounts indeed for the target KPIs. But not just that, the different versions will be selected also having in mind the level of complexity, that is the amount of computational resources that will be needed to execute this model at the node. So the DRL agent makes its own decisions, and then the aggregator is the one that aggregates the different selected versions of the model and create a unique model that is delivered to the radio interface, where, of course, the model will be used for decision making for the different radio functions at hand. Now, this is the impact on the system KPIs that can be achieved through merge. Whenever the KPIs, for example, are latency or packet loss, we can see here that after a transient period, this refers to the case of a reinforcement learning model that is created. The model indeed is able to meet the target KPIs. And when we compare merge against alternatives, the RAD is the centralized one that is supposed to perform the best. And then we have federated learning and the case where we select just one pruned model that is suitable for the availability of the computational resources at the node where the model has to be executed. And phi A represents the amount of resources that are available at that node. We can see that merge outperforms the other approaches and matches essentially the RAD that is supposed to be indeed the optimal one. So in summary, we can consume less computational resources, about 50% less, for a given consumption of computational resources. We can get through merge 20% better decision-making performance with respect, for example, to the case where we select just a single model that is compressed in such a way that can be run at the node where inference needs to be executed. In terms of energy consumption, we have also great performance. Over 30% reduction in the energy consumption during training and a 50% reduction in energy consumption due to inference. And this is compared to the centralized and the federated learning paradigms. Now, we developed merge and we included in the design of the pipeline that has been created within the project. Please refer to POC 3 for the development of this ML Ops pipeline. Here we have a new request that arrives, and it's the orchestrator engine that is the brain of the system that makes decisions on how these requests should be fulfilled. Within the orchestrator engine, we have the AI/ML model selection where merge can be put in action. Here we get information about the resources that are available at the node where the model should be executed, so inference should be executed, and we get information about the versions of the model that exist in the system from the repository and the associated catalog. And then we can select and create the model to be then deployed thanks to this pipeline manager that performs resource and agent deployment, and then the model can be used. I would like also to mention that colleagues from Nextworks realized a nice demo that represents and demonstrates this pipeline. And with that, I thank you for your kind attention, and here are our contact information. Thank you.